In this video, we're going to conclude section 7.3, and what we're going to be doing is looking at very systematic procedures for drawing Lewis structures of covalent compounds. This is a really important skill to develop, and you're going to be doing lots and lots of Lewis structures in the upcoming sections. And being realistic, it isn't uncommon to have to do 10 or so of these Lewis structures in a test. So you really do want to make sure that you've got this procedure perfected. So in a Lewis structure, what we assume is that the total number of valence electrons in a molecule or a polyatomic ion are going to be shared so that every atom has a share of 8 electrons, that is, that it has a noble gas configuration. The only exception to this is that hydrogen is happy if it has a share of 2 electrons so that it looks like its nearest noble gas, helium. The procedure for writing a Lewis structure for a covalent compound is a 6-step process, and the very first step is to count up the total number of valence electrons that you have to work with. Now, the valence electron of a main group element, which is what we'll be dealing with here, is just simply equal to its group number. So I'm going to illustrate writing a Lewis structure for a covalent compound with carbon tetrachloride. So carbon is in group 4 and can contribute 4 electrons, and then I've got 4 chlorine atoms, each of which is in group 7. So 4 plus 28 gives me 32 electrons to be working with. So the next step in this process is I have to decide the basic layout of the atoms in my molecule or ion. And there's always going to be one central atom and then multiple, well, theoretically multiple, we're going to look at up to 6 perhaps, outer atoms. So we want to be deciding what atom's going to go in the middle and what atoms are going to go on the edge. And these are the things that can help you. Hydrogen is always an outer atom. It always goes on the outside of our molecule. And then what you want to look at once you've kind of confirmed what has to be an outer atom is what atom has to be in the middle. And the element with the lowest group number will be the central atom. And if there are 2 elements that are in the same group, then it's going to be the one that is lower down in the periodic table that will be your central atom. So a good example of this is if we have a compound like sulfur trioxide, both of these guys are in group 6, but sulfur lies further down, it's in period 3, versus oxygen that's in period 2. So sulfur will be my central atom and my oxygens will go on the outside. Now it makes sense that the atom with the lower group number goes in the middle, because as we move to the left of the periodic table, you'll see that we get more octet vacancies. That is, we want the atom that needs to form the most bonds to go in the middle. So in our example compound, carbon tetrachloride, carbon is in group 4, chlorine is in group 7. So therefore carbon is going to go in the middle, and so we know that the chlorines will be on the outside. So now we've got the general layout of our molecule. We just have to put in all of our bonds and any non-bonding electrons. So we've got 32 electrons to make all of our bonds with. So the third step in drawing a Lewis structure is, now I've identified my central atom and my outer atoms, is I should connect my outer atoms to my central atoms by single bonds. And I have to do this because every outer atom has to be connected by at least a single bond. So we'll just go ahead, and once you've got your outer atoms and your central atom identified, you can draw in single bonds, because you have to have at least single bonds tying everything together. And then the important thing to do now is you've got to subtract away 2 electrons from your total for every single bond that you draw. So now I've got 24 electrons left to finish everything off. So what I'm going to do in step 4 is I'm going to add what we call lone pairs. These are those non-bonding electrons to complete the octets of all of my outer atoms, and then I'm going to subtract that from the total. So I had 2 from the bond, 2, 4, 6, 8. So I need 3 lone pairs on every chlorine atom to finish off the octet. So after making the bonds, I had 24 electrons, and then I add 6 to each of the 4 chlorine atoms, and that gives me 0 electrons left. So what that means is, if I don't have a valid Lewis structure at this time, because I've got no more electrons left to work with, all I can do to finish off this Lewis structure is move around where the electrons are. Once my count gets down to 0, I can't add in any more electrons to finish this structure off. So the first thing that we're always trying to do is to get our count of electrons down to 0 before we move on. Now, the 5th step in drawing a Lewis structure of a covalent compound is not always needed. The 5th step is, if you have any electrons left over after completing the octets on the outer atoms, then you add them as lone pairs on your central atom. And at this point we don't. We started with 32, we subtracted 4 lots of 2 for the bonds, and then we subtracted 4 lots of 6 for the lone pairs on the outer atoms, and we have none left. So we don't need to do anything in step 5 in this case, and that's not that uncommon. The 6th step in drawing the Lewis structure of a covalent compound is to check our central atom and see if it has an octet. So in our case, 2, 4, 6, 8, it does, and we don't need to do anything for step 6. But if you have a compound and your central atom doesn't have an octet, what you're going to need to do is, because you can't add in any more electrons because your electrons have all been used up, what you're going to do is bring in electron pairs from the outer atoms to form either double or triple bonds until your central atom has an octet. And I'll do an example of that in a moment. But the key thing here is, don't ever make double or triple bonds and if you haven't used up all electrons. So don't even think about making a double or a triple bond unless your electron count is down to 0 electrons. If you do, your Lewis structure is guaranteed to be incorrect. Okay. The last thing that we need to keep in mind, which becomes important when we're considering step 1, is if the thing that you're trying to draw a Lewis diagram for has a charge, then you have to add in electrons for every negative charge or subtract away an electron for every positive charge in order to get the correct count of valence electrons. So I'll give you an example here. This is the ammonium ion. We get 5 electrons for nitrogen because it's in group 5. We got 4 lots of 1 electron for the hydrogens because hydrogen's in group 1a, and then we have to subtract 1 away because it's got the 1 positive charge, and then that gives me 8 electrons. For an anion, it's a similar thing, but now we're going to add 1 electron for every negative charge. So again, we get 5 for the nitrogen, 3 times 6 for the oxygens because they're in group 6, and then we add in an extra electron for the 1 negative charge, and that gives us 24 electrons. So just a tiny little thing to be aware of if you're doing this for a polyatomic ion. So now I'm going to give an example where we have to use the final rule where we make double bonds. So we're going to draw the Lewis structure for carbon dioxide. Carbon's in group 4. The 2 oxygens are in group 6. So when we add all of that together, 12 plus 4 gives me 16 electrons. Now, because carbon is in group 4 and oxygen is in group 6, I know that carbon will go in the middle and oxygen will go on, and the oxygens will go on the outside. I've got to subtract away 2 electrons for every bond formed. So I'm down to here now. Step 4 was to complete the octets on the outer atoms, and in this case I'm going to do that by adding 3 lone pairs to each of the oxygens, and if you keep count, that uses up all of my electrons. So when I get to this point, I've got no electrons left. Now step 5 was after step 4 I had some electrons left, I should put them on the central atom. So I don't need to do that because there are no electrons left after step 4. Then step 6 was form 2 double bonds. Rocky decided that was the perfect time to bark there. Okay, so getting back to it, step 6 is says that we should move in electrons from the outer atoms in order to ensure that the central atom has an octet. So after step 4, I was at this point here, and I had no more. At step 5 was place any extra electrons on the central atom, which I can't do because I don't have any electrons left. And then step 6 is I've got to check my central atom and see if it's got an octet. 2, 4, it doesn't. It's only got 4 electrons around it, which means I need to bring in another 4 electrons. So I'm going to bring in 2 there, and I'm going to bring in 2 there. And so those guys are no longer lone pairs, and now they have become shared electrons. Now, what you want to do is you want to bring these lone pairs in symmetrically. So you bring one lone pair in at a time from each of the outer atoms. Later on, we'll get more complicated, and we'll give you, when there's an ambiguous situation as to what electrons to bring in, we're going to give you some rules as to how to deal with that. But for the moment, you just bring them in from one atom at a time until your central atom has an octet. So let's go through a few sort of practice problems. Here we're counting up the valence electrons, which is step 1 in our procedure. So we've got 2 nitrogen atoms here, and nitrogen, if you look on the periodic table, is in group 5A. So we've got 10 electrons to put that molecule together. Carbon monoxide, carbon is in group 4A, so can contribute 4 valence electrons, and oxygen is in group 6A, so that's also going to be a 10 electron molecule. This molecule here is called methane, or some people say methane. So carbon is in group 4, and then we have 4 hydrogen atoms, and hydrogen's in group 1A, so that's an 8 electron molecule. These guys are going to have, we've got 2 atoms, and we've got 10 electrons to form the molecule, so we would expect them to have similar diagrams. This is going to be very different. We've got 5 atoms, and we've only got 8 electrons to form all the bonds. Okay, the last one here is the carbonate anion. 4 electrons for the carbon because it's in group 4A. And then we've got 3 oxygen atoms, and they're in group 6A, so they each contribute 6 electrons. And then we have to remember to put in the 2 electrons for the charge. So 4 plus 18 gives me 22, plus another 2, 24 electrons. When it comes time to identify the central atom, you've got to go with the lowest group number. And if the same group number, it's the biggest period or the highest period. The other rule that we had is hydrogen is always an outer. That can save a little bit of time. So in the first one here, hydrogen's going to go on the outside because it always does. Oxygen's got to go in the middle. In this one here, sulfur is in group 6A. Oxygen is also in 6A, but sulfur is lower down, so sulfur goes in the middle. And this compound here, carbon tetrachloride, we've already done this one, haven't we? Carbon is in group 4A, chlorine is in group 7A, so carbon has got to be our central atom. For the carbonate anion, carbon again, group 4A, oxygen, group 6A, carbon is our central atom. So sometimes what you'll see is you kind of start to notice a pattern after a while that when we have only one of an atom, it is frequently the central atom. You should still check, but if you're running out of time, that's a good guess, is that if you've got one of the atom, it is. Sometimes you'll see that some people go with the rule that, or the guideline, that the first atom in the formula is always the central atom. It doesn't really work that well. The best thing is to use the official rules of the lowest group number, but if they're in the same group, go with the highest period, and then hydrogen's always on the outside. Those won't ever lead you astray. Some of these other things that are meant to work don't always work. Okay, so let's draw some Lewis structures now so you can see how that works. I'm going to do O2. So I've got 2 oxygen atoms, and they're both in group 6, so that gives me 12 electrons. So what's my outer atom? Is it oxygen or is it oxygen? Well, guess what? It's oxygen. And I'm going to join that to the other oxygen. So that's going to give, I've got to take away 2 electrons, and that's going to leave me with 10 electrons to finish everything off. And then I've got to complete the octet on my outer atom. Here we go, 2, 4, 6, 8. So I'm going to take away 6 electrons, leaves me with 4 electrons. Place any leftover electrons on my central atom. So no electrons left. Check whether my central atom has an octet. 2, 4, 6. It doesn't. It's 2 electrons short. So what I've got to do, bring those guys in. They're not a lone pair anymore. They become a bond. So that's the first one. So oxygen, got a double bond in there. Okay, got a space. Next one, methane. 4 electrons for the carbon, because carbon's in group 4A. And then we've got 4 hydrogens, and they're each in group 1A. So I've got 8 electrons total to do here. Hydrogen is never an outer atom, so never the central atom. So it's got to be carbon. And my molecule looks like that. And then I'm going to subtract away 2 electrons for each of the bonds I form. And that gives me 0 electrons remaining. So for hydrogen, it's happy if it's got a share of 2 electrons. That gives it a noble gas configuration. So hydrogen's got 2 electrons, hydrogen's got 2 electrons, hydrogen's got 2 electrons, hydrogen's got 2 electrons. So those guys are happy. Now I check whether my central atom has an octet. 2, 4, 6, 8, and the carbon is happy as well. So I'm done with that. I didn't, I basically stopped after step 2. So that was nice and easy. Okay. The third one over here, water. You can kind of start jumping to the general layout after a while, because we know that hydrogen's going to go in the middle. So we've got 6 electrons for the oxygen, and then we've got 2 times 1 electrons for the hydrogen. That gives me 8 electrons. We form 2 bonds, so I've got to take away 2 lots of 2 electrons, and that leaves me with 4 electrons remaining. The hydrogen already has its complete octet, so I can go ahead and place those electrons on that central oxygen there and take that away. And you'll see that every atom now has a complete octet. 2, 4, 6, 8. The oxygen's got 8, and then the hydrogen is happy with 2, and hydrogen's got a share of 2 electrons. Okay, this compound here, CH2O. So when I think about what is going to be the central atom here, I know it's not going to be hydrogen. So then it comes down to whether it's carbon or oxygen. So carbon is in group 4 and oxygen is in group 6. So carbon is going to be my central atom, and everything else goes on the outside. So I can normally get a kind of general layout of the molecule just by looking at the group numbers. Okay, so now let's go ahead and count up our valence electrons. We've got 4 for the carbon, 2 times 1 for the hydrogen, and then 6 for the oxygen. So it gives me a total of 12 electrons. Now I'm going to use 3 lots of 2, or 6 of those, just to make the bonds so that everything is attached. So I'm at step 3 now, I think. So what I've got to do now is complete the octet on my central atom here, or step 4, and so on my outer atoms here. So hydrogen is happy with 2, because it's got 2 shared electrons there, and then the oxygen only has 2 and it wants to get to 8, so I've got to put 3 lone pairs on it. So take away 6 electrons and that leaves none. So now what I've got to do is check whether my central atom has an octet or not, and it's got 2, 4, 6. So I'm going to need to bring in 2 electrons. So there's only one place I can bring them from, and that's from the oxygen. And there we go. So we end up with a double bond in this case. The oxygen's got 2 lone pairs on it, and then the hydrogens are attached via single bonds to the carbon. And so that's it. They're kind of some examples there. Alright, so I would like you to do these end of chapter exercises, and then I'll be available to help you Wednesday via Zoom.